Before we look at special relativity theory, let's look at Galilean transformation. And after Galilean transformation, we look at Lorentz transformation. First of all, let's define frame of reference. Frame of reference is the coordinates that describe the position of an object, sets of coordinates. Space and time coordinates, in this case we're looking at x, y, and z, that's space, and t is time. So frame of reference is a set of coordinates. Example, x, y, z coordinates and time. Galilean transformation is used to transform between the coordinates of two frames of reference which differ only by constant relative motion of Newtonian physics. That's referring to classical object, in this case where the speed is small compared to speed of light. So that's for you and me traveling with the speed. If you have two frame of reference here, both initiated from the same point, and S is going to be stationary, S prime will be traveling with a velocity v, and both have their y and y prime, which are parallel, x prime and x are parallel, z and z prime are parallel, and so they both have initial starting point of 0 and 0 prime, where t will be equal to t prime because that velocity is going to be slow. So we have the s stationary at rest and s prime with a constant velocity moved a distance x dot. So that frame of reference has moved a distance x dot, and the x dot, we know what speed is. Speed is v, which equals to x dot over t, and therefore x dot equals vt, and that's what we've got here. That frame of reference and that frame of reference distance is x dot, and this is equal to vt. And if an event happens at here in the frame of reference of s prime, which is moving with a constant velocity v, the object A in the frame of reference of S, we see that event from a distance of x, and that distance will be equal to the sum of the distance of x dot plus the distance where the event happened in the frame of reference of S prime, which is x prime. And so that plus that will be equal to x. And don't forget that the velocity of this object is small, very small compared to speed of light. C is speed of light and v is the velocity of the frame of reference. So now we need to find the position or the x equation. And if we write that x equation for this event happening here, we would get that x is equal to x dot, that distance here, plus x prime. And therefore, we can then say the x is equal to vt plus x prime. And the vt is that one here, because x dot is equal to, or v is equal to x dot over t, and therefore x dot is equal to vt. We can rewrite that equation by saying x prime is equal to x minus vt. Y prime, or y prime will be equal to y, z prime will be equal to z, and t prime will be equal to t, because there's no motion in the y direction, nor there is motion in the z direction. So the velocity when the event happens from s will be vx, because it's from event from s, will be equal to v, which is the frame of reference of s prime, plus the velocity that happened at the event which they moved on, which is vx prime. The vy will be equal to vy prime, and vz will be equal to vz prime. The acceleration will be the same for both cases because that's changing velocity, and therefore the ax prime will be equal to ax, and ay prime will be equal to ay, and az prime will be equal to az. So this is the Galilean transformation of two frame of reference, where one is stationary and the other is moving with a constant velocity. And this is the velocity transformation, and this is the acceleration transformation. So the Galilean transformation with the distance or space and time, and this is the velocity transformation and the acceleration transformation. But this transformation is not compatible with special relativity, and that's why we're going to look at Lorentz transformation, which is compatible with special relativity theory.